Hello again. We are going to start a new topic today. This topic is a continuing quest in our long quest this semester to find some kind of data structures that will make it faster to do search, insert, and delete in large tables of data. Now, this table I took from the Princeton site that I listed there. It gives a summary of much of what we've done so far. We've looked at unordered arrays, unordered linked list, ordered linked list, binary search trees. We haven't done randomized BSTs, nor have we done red-black trees. A red-black tree is just another kind of tree like the AVL tree we did. Also, this does not show B plus trees. Well, they're all okay, but believe it or not, there's a technique that if we could make it work, it would take us only one search to find something. Inserting and deleting would be pretty easy, and searching would just say, look in this particular spot. Now, that's called an order one. It says it's a constant algorithm. That means no matter what the input is, you get the same amount of effort. It takes essentially the same complexity. That item, I won't hold you in suspense, is hashing. Hashing is a technique that simply says, please ignore the cat. She has had plenty to eat. She just seems to want to be on video, from what I could tell. The idea of hashing is to create a positive integer valued function from whatever we put in. So if you're putting in, say, telephone numbers and people's names, the key might be the telephone number. And so you're going to take this key and you're going to do something to it. Some kind of arithmetic, who knows what. And you're going to end up with a number, a positive integer. And you're going to take that number and you're going to go to a table that you've created, a huge storage area in memory. That's all I mean by a table. And you're going to put the value. If you're inserting, you're going to put the value there. If you're searching, you're going to see if there's a non-zero value there. And if it is, it's in the table. And if it isn't in the table. Well, that would sure be nice. But the only place it works is Utopia. Unfortunately, what do we do if two keys produce the same value? And it's very hard to prevent that from happening. Now, here are some examples of hash functions. We could take all the digits and add them together. So I used the telephone number there that has a area code in it. It's 10 digits. So the largest number I could get is 90. That would give me only 90 places to put the pairs. And surely we would get duplicates. Only 90 might be a very small telephone address book that you have, but certainly not for a big metropolitan area or something. Second try, add the squares of the digits. Well, this time we could get 81 in each place. We have 10 places, so we get 810 places. Well, that's doing better, but it's still not great. Third try. Label the digits 0 through 9 starting on the left. And take the sum of 1 times digit 0 plus 5 times digit 1 plus 5 squared times digit 2 plus so on. Well, that gets pretty large. I've just given you one example there. And we would probably consider it too large So we'd put a mod on it and take it, say, to 4096. Now we would have 4096 places to put our pairs. That method is the kind of hash functions we might use. We want a hash function that uses every digit in the key. I said character there, but look at that as everything in the key, every individual piece. We might multiply the key, add parts of the key, multiply parts of the key by random numbers. We might take the mod or something. We might take the middle digits. There are all kinds of ways that we can do a hash function. Our goal is to have something that's easy to compute because we're going to have to do it so many times. Now, before we figure out a hash function, we have to know how much space we want. Let's say that we decided that a name of a person, we wouldn't allow more than 10 characters. That would leave most people out, but that's okay. Then the third scheme would mean we need to allocate 10 bytes, because a character takes a byte, for 4096 places, which is over 40K. And we might even say we want a bigger place. We want to leave some of these empty. In other words, the more space we can have, the less chance we have of having a clash, a collision, two things that go to the same place. So this is a very classic example of a trade-off. We might want to have a lot more spaces than we actually expect to have keys. That way, we would have empty spaces. Well, let's see. One thing that's often used in handling the kinds of hash functions are the bitwise operations. So far, I don't think you've done bitwise operations in 103 or 104. I don't even think you've done them in Python if you've had that. These operations operate on the internal representation of an item. We look at things from the outside. We see integers. We see floating point numbers, doubles. We see char. We see strings. The computer doesn't. The computer sees strings of zeros and ones. That's all it sees. The software, the program, has to interpret what those zeros and ones mean. The only place where you may have done this up to now is when we talked about strings way back in CSC 103. And we talked about the ASCII code, where each string had a set of eight ones and zeros that represented it. In the computer, 1 byte is usually said is an 8-bit string. So think of it always 8 bits, 1 byte. That's pretty standard. It was different maybe 25 or 30 years ago, but it ain't now. Just about everybody has 1 byte, I believe, is 8 bits. We also have a concept called a word in a computer memory, and a word is 4 bytes. So since we have 8 bits in a word, in a byte, 4 bytes in a word, we have 32 bits in a byte. 4 bytes are usually used to represent an integer, unless we try to save space by declaring short integers, or unless we have large integers and we make them long. But traditionally, in most computers, 32 bits is an integer. That is the reason there is a restriction on the size of an integer. The largest integer you can have is a string of 31 ones and a 0 in front of it to tell you that that's a positive number. And that number just happens to represent 2 to the 31st minus 1 if you interpret it as an integer number. So there's always a restriction on the sizes. Now, let's look at a little setup here. First of all, long strings are very hard for us to understand. Once you see 32 ones and zeros, and then see another one, and then another one, your eyes glaze over after a while. So the computer world has tried to come up with a compromise. What they've done is said, we won't use base 2, which is what binary is. We will use base 16, which we call hexadecimal. But luckily for us, turning hexadecimal into binary is trivial. We just start at the right, and every 4 binary digits, we substitute the hex digit. Now that's because 0 represents 0, and so do 4 zeros. 1 represents 1, and so does 3 zeros and a 1. 2 in hex is 2 times 1. In binary, it's 1 times 2 plus 0 times 1. In other words, in binary, we're going to use the powers of 2 instead of the powers of 10 as we represent our numbers. In hex, we're going to use the powers of 16. So, for example, 6 is represented as 1 times 2 plus 2 times 2 squared, 4 plus 6. 9 is represented as 1 times 2 cubed plus 1, or 9. We run out of digits after 9, so we use the first 6 letters, A through F. So F represents 1111, and that's the largest value you can get in 4 digits. You can't go higher than that. If you want to go to 16, you're going to have 5 digits. You're going to have 1 and 4 zeros. So that is the way we'll look at a lot of things to make it easier. So, for example, I showed you what A is, because A is represented by 4-1 in hex, and then I converted 4-1 to binary. We've had a lot of operations in C++, but now we're going to have a set of more of them. Actually, I think 4 or 5 of them. 4. And these operate on bits. 2 of them, or 3 of them, look very familiar. X and Y, XOR Y, and not X. They work exactly the way that X and Y and X//Y and not X work for integers or for other, for almost anything else, for truth values, T and F. The table's the same, and you can look at it. N requires both of them to be 0. I think I wrote both of them to be 1, so you can think of 1 as true, or requires any one of them to be 1, or both of them 1. Not simply flips a 0 to a 1 and a 1 to a 0. And we have another special one called XOR. That stands for exclusive OR. And it says that it's only true, it's only 1 if one and only one of the two bits it's working on is 1. That one would be nice to have at a higher level too. Now, the operations work bitwise. So if W were 0110 and Z were 1100, then I'd take, for the OR of it, 0 or 0, 0 or 1, 1 or 1, and 1 or 0. So you just go one at a time. Now there's another operation that is very important. And this is an operation that moves bits around. As I said, the bits are 32 bits in a word. Let's say you want to shift the bits towards the left or towards the right. Then you use the operations that look familiar from input and output. This is a right shift. It says, take this and shift it right 5 times. As we shift it right, we add zeros. 1, 2, 3, 4, 5, and then the number we had over here. When we're shifting right, we fill in with zeros. When we're shifting left, for us, we will probably be filling in with zeros. However, we have to be careful. That's only true for positive numbers. The way the computer represents a negative number is it puts a 1 in the last place, the leftmost bit. Now, it also does some other things. So you can't just say it puts a 1 in front of the positive value. It represents it as 2's complement, which you'll learn about, I think, in architecture, but not now. And you'll notice you have the opposite shift, the opposite that we use, the 2 chevrons. Normally, we fill in with a 0, and that works out for us. Now, I wrote a little program, which I have here, that shows some of these. It's down below here, so you can practice it and look at it. One of the things I had was bitset, because bitset allows me to write things out in bits and in hex. Bitset N in front of something I'm going to write out says how many bits I want in the output. Hex in front of something I'm going to write says I want the next thing in hex. Now be careful. Hex is in effect until you turn it off. So there's another word called dec, D-E-C, which turns it back into writing decimal. So here's the program, my output from it, and I suggest you run it and take a look at it, put in some numbers of your own and see what you get, and see if you can understand how it's working. And I have a file here that I put in a program to play with it. This is sort of a hash function to take a look at. It's just one to play with. We'll write better ones, I hope, soon. So that's what I want to start talking about today. We're going to have more information on hash. I do have a little bit of a homework for you to do, but it's mostly to learn about the bit functions, since they're used a lot in hashing. So let me show that homework to you. There it is. I want you to take a program. I want you to take a file. Now, I wrote this out because I want to make sure that you understand what I want instead of, you seem to be having so much trouble with algorithms this semester. I thought I'd write it out in some detail. You're going to declare a character variable and an unsigned integer variable. That means unsigned int. you're going to repeat the following. Read the unsigned integer. Print the variable in binary. That's the bit set. Now, if the unsigned variable n, that's 7 zeros and a 1, that turns out to be 32 bits. And the only one of them that's a 1 is the rightmost one. Print 1, else print 0. Then when I'm asking, and then read the character variable and keep doing this until the character is y. By the way, none of you seem to be remembering the do while, which would be perfect for this particular structure. Now, I want you to think about, what does this tell us about the bits of the unsigned integer? Does it tell you the value of any particular bit? Is it possible that you're finding out the value of a particular bit by doing this? Then I want you to go a little further. Now I want you to take the program and part B, pardon me. And this time I want you to move it 3 to the right. So that means you move 3 digits off the right. Now, what does that tell me? Does that tell you about any particular bit in this particular variable that you read in? And then think of those two and write this program, which I did not give you the algorithm for. You're to read in an unsigned integer the same way as you did up here. In other words, you're going to have it looping. And I want to count the number of bits, number of ones in the binary representation. For example, 765 is represented by this ugly number. And if you count it, there should be 8 bits in it. 3 is represented by a much prettier number, and there are 2 ones in it. Then again, I have another number, and I have how many bits it has in it. To do that, you don't need a lot of fancy stuff. You have most of it up here in this area, in these areas. You probably need to figure out how to put a loop somewhere to get what you want. But don't make it massively difficult. It can be pretty simple. You can do it using only the and the shift as far as those operations are concerned. And of course, you'll have to use the if statement and an addition for the adding to the count. So that's it for now. I'll be posting the video and I'll be putting these out. See you later now. Bye.